Let's have a look at semiconductors. Semiconductors are components such as diodes, transistors, integrated circuits, and they are integral to everything in modern day life. I want to start by just looking at some simple elements. For example, a conductor. A common conductor would be copper, and its atomic structure is 2, 8, 18, 1. In the outer shell of copper, there is one electron, and it is that one electron that makes copper a very good conductor. And if we move that electron away, bearing in mind the electron is negative, if we move the electron away, then it leaves a hole behind it, and a hole is positive. We need to think about that in a little while. So that was copper, a good conductor. If we move on to thinking about an insulator, then insulators will tend to have 8 electrons in their outer shell. That means their outer shell is full, and it's very difficult to break that outer shell and make it become a conductor. And this would be materials such as PVC, polyvinyl chloride, or perhaps glass. These are compounds which basically produce excellent insulating properties. But here the outer shell electrons, so there's your outer shell, the outer shell electrons are 8, the outer ring is complete, and that makes it an insulator difficult to break down. So let's move on to something that is between a full outer ring and just one electron in the outer ring, the outer shell. So let's talk about a semiconductor material. The most common material we use for semiconductors is silicon. Just going to change the pen. So silicon is the most common one that we use, and its atomic structure is 284. So we would think because there isn't 8 electrons here, then this should be a conductor, and that would be perfectly reasonable. So the outer shell has 4 electrons, so we think it would be a conductor. But the fact is, it isn't. Let's look at that now. If we consider pure silicon, and this diagram represents just the outer shell electrons, then silicon does something that isn't too unusual in the world of chemistry and physics. Basically, it shares electrons with its neighboring atoms. So this is called a lattice, often referred to as a diamond lattice. But pure silicon shares neighboring electrons, and that gives the impression that at any instant in time, the outer shell of every atom has 8 electrons in it, and therefore pure silicon is an insulator. Let's just label this up. This point of sharing is called a covalent bond. And that is important. So we need to remember that pure silicon is an insulator because of the covalent bonds and the sharing that takes place. So we're into some very, very clever science, which we don't need to dwell on, unfortunately. But let's consider some other elements. For example, if we look at aluminium, aluminium has an atomic structure of 283. So we have its shells, orbits, rings, whatever you want to call them. So this has only 3 electrons in its outer shell. We'll come back to that in just a few moments. Let's look at another element, in this case phosphorus, and its atomic structure is 285. So the numbers 3 and 5 are significant to us, and we're going to use these in the slides, in the sheets that follow. So bearing in mind that pure silicon is an insulator, with some very, very clever science, the scientists have made it possible to make silicon conduct. So here we've created a mixture. We have a mix of silicon and aluminium. So aluminium has been blended into the silicon to make a compound. And what happens is this. The outer shell electrons will form covalent bonds wherever possible. So that lattice structure is still very similar to how it was before, but with one difference. Aluminium has only 3 electrons in the outer shell, so here there is something missing, and this particular atom cannot form a covalent bond and it cannot link up. What we've created here is a hole, and if you recall from basics in previous parts of the course, a hole has a positive charge. So just summarising what we have, a piece of silicon which has added aluminium will have an overall positive charge because it's got extra holes in it. So positive charge, we call this P-type semiconductor material. So it has a complementary partner, and that's going to be N-type semiconductor. If we have a look at this, here we add in phosphorus. So the scientists have produced a compound which starts with silicon as the base, and we've added in phosphorus, and covalent bonds will form. And hopefully you can see that here we have a difference. This electron is bilinomates. It has nowhere to form a bond with. So this electron, bearing in mind that an electron has a negative charge, this electron will not form a bond, and it's free for us to detach and make it move. If we have a piece of semiconductor material, so it's silicon with extra electrons in, it has a negative charge, so we call it N-type semiconductor material.